Hi, I'm Sheng-Han, and this is my optional assignment for ME557 course. Today I'm going to talk about design for sheet metal working and cost estimation for individual dies. And this page is the table of contents. Here I would include types of sheet metal working, cost of individual shearing dies, individual dies for bending operations, and individual dies for deep drawing in the following content. And sheet metal working is also known as metal sheet stamping process. The reason why I would like to talk about sheet metal working is that this is a common manufacturing process, which can be seen in a lot of space. I will show some examples in the next few pages. And here's the link that introduces a metal sheet stamping process. Also, the content here is based on the same book used in class.
Today, we're going to be looking at the process of metal stamping, some of its uses and applications. Metal stamping involves the use of a press machine equipped with dies, which are specifically designed tools that shape and cut the metal. The metal sheet is placed between the dies, and pressure is applied to form or cut the metal into a desired shape. Metal stamping can be performed on various metals, including steel, aluminum, brass, copper, and stainless steel. The material selection depends on the specific application and the requirements of the part being produced. Some of the advantages of metal stamping are the high production rates, accuracy, and cost effectiveness for large volume manufacturing. Additionally, it can be easily automated for increased efficiency. Tooling and die design are critical aspects of metal stamping. The dies are custom made to match the desired part's shape and specifications. The design process handles material thickness, part complexity, tolerances, and production volume.
In this page, here is an example of sheet metal working in the real life. Here's an image of a car door, as you can see, done by the metal sheet stamping process. And here is the reference down below. Here is another example. This is a computer's frame, and this is also done by metal sheet stamping process. As you can see, there are lots of bendings and like some protrusions from a sheet metal, and the reference is also down below. From this page, I would like to start to discuss of different kind of part design. And the first one is the cutoff part design. The use case is when parts have two parallel edges and can be jigsawed together along the strip. It can be called as a cutoff part design. And among all the design, this is the most efficient in terms of scrap minimization and tool simplicity. And the scrap of this kind of part is the edge scrap from cutting full sheets into strips and from strip ends. And the design limitation would be limited to symmetrical jigsaw-like part shapes. And here's a figure from the book showing what cut-off part design is. Next, in this page is the part of part design. The use case is it also used for parts with two parallel edges, but where the ends cannot jigsaw together. As shown in the figure, it's different from the previous one. They cannot jigsaw. It's quite obvious, and it allows more varied part and shapes compared to cutoff. However, the scrap is slightly more than cutoff parts because they must be separated by at least twice the sheet thickness to preserve punch strength. And also, tooling is slightly more complex than cutoff due to need for an extra die block. And here's a figure showing what part of part design is. In this page, figure A shows how it looks like to be a cut-off part design. As you can see, by punching the sheet metal, the part will directly come off to the left. And for figure B, it shows what part of part design looks like. There will be some scrape get down below, and the part will come out at the left. After taking a look at cutoff and part of part design, we started to look for more complex shapes, which we introduce blanking die. So the use cases for parts with non-parallel edges or complex external contours that cannot be formed by cutoff or part of dies, we will use this kind of die, which is blanking die. And it has very high design flexibility, allows nearly any closed shape. For example, like circles or irregular outlines. However, the scrap is the highest among all the three. Each part requires spacing from the strip edges and adjacent parts. And also, it costs more and will have higher setup time. And here is the figure showing blanking die. Next, I would like to talk about the cost of individual shearing dies, which is cost estimation of these dies. And the first parameter that I would like to talk about is CDS. And CDS is called die set purchase cost, which is measured in dollars. And CDS equals to 120 plus 0.36 AU. And AU is the usable area, which is in centimeters square. Another parameter is MDS. And MDS is the die set manufacturing hours, which is measured in hours. And as you can see, if you multiply the MDS formula with $40 per hour tool making rate, you will get the CDS formula. So basically, it's the same, and you can change the tool making rate to adjust CDS. The next parameter is XP. XP is the profile complexity, and XP is equals to P over the square root of LW, and P is perimeter, which is the length to be sheared and measured in centimeters. LW are the length and width of the smallest rectangle that surrounds the punch, which is also calculated in centimeters. And profile complexity is surely important because the complexity of the part will affect the cost of the dies, which is the parameter that we need to consider. And the last parameter in this page is MP0. And MP0 is the basic die manufacturing hours associated with perimeter complexity. And as you can see, we just plug the XP that we get from the previous formula into this equation. And MP0 equals to FD times 28 plus 1.03 XP. And FD is the die type factor. For blanking die that we mentioned in the previous slide, the FD will be 1.0. As for the part of die, FD will be 0.91. As for the cutoff die, FD will be 0.88. After talking about those parameters in the previous slide, we started to estimate the manufacturing points for individual shearing dies, and which is the parameter MP. And MP equals to FP times FLW, FD, MPO plus MDS. And as you can see in this slide, FD we have discussed in the previous slide, and FP, FLW, and MPO are the ones that we haven't discussed yet. We will discuss in the next few slides. And as for FP, it's called die plate thickness correction factor. FLW is the plane area correction factor. For MPO, it's a basic manufacturing point. As for MDS, as we discussed previously, is a die set manufacturing hours. So in this slide, we will start to understand how to get each parameters from for the formula in the previous slide. And first, we will need to know how to calculate FP. So FP is the die plate thickness correction factor. And to get FP, we need to get HP. And HP is the recommendations on die plate thickness, which is shown in the equation right here. And for each parameters, U is the ultimate tensile stress of the sheet metal to be sheared, and UC is the ultimate tensile stress of a new low carbon steel. As for V, it's the required production volume expressed in thousands. As for H, it's the sheet metal thickness, which is measured in millimeters. And after plugging these parameters into the previous formula, we get HP. And by using FP equals to 0.5 plus 0.02 HP, we will get FP, and then we can plug into the MP formula. And next, in this page, we would like to see how to calculate FLW, which we will need to use in the MP formula. FLW is the plane area correction factor, and in figure 9.9 from the book, and here you can find how to use the area correction factor in the y-axis. For example, if you calculate XP as 3 and the plane area of punch is approximately 400 square centimeters, and you can imagine the correction factor will be around 3 to 4. And for another example, if you have XP equals to 15 and you have a plane area of punch at around 1300, and you can get the correction factor at around 9. This is how we find FLW, and then we can plug it back to calculate MP. Next is how to calculate MPO. And MPO is the basic manufacturing point, which is determined by the profile complexity. And profile complexity is XP, as shown in the formula on the right hand side. And when you get the profile complexity, you can get basic manufacturing points MPO, which is the y-axis. Next, I would like to talk about individual dies for bending operations. There are basically 4 types of die, And the first one is the V die. And it can perform single bend, and it is low cost. However, you cannot determine the precise position of the sheet metal. Therefore, it is not really precise. And on the right hand side, this is called wiper die, which is the second type of dies for bending operations. And also, the wiper die can perform a single bend. And since you can control the location of the sheet metal, therefore you can get a precise bending. For another two types of individual dies for bending operations, the first one is the U die, which is shown on the left. And the last one is Z die, which is shown on the right. And these dies can perform multiple bends in a single press stroke, which is more efficient than those two that we mentioned in the previous slides. Next, in this slide, I would like to talk about the cost estimation for individual dies for bending operations. And same, we need to have the total manufacturing points, MP. And after a lot of calculations on the book, the MP for bending operations is basically equals to 21 plus 0.032 LW plus 0.68 LB plus 0.58 MB. LMW is similar as the previous one, which are the length and width of rectangular that surrounds the part, and also still measured in centimeters. As for LB, it's the total length of bend lines and also measured in centimeters. As for MB, it is the number of different bends to be formed in a die. And with these parameters, we can get the total manufacturing points of MP. And after getting all the manufacturing points, how are we going to calculate the cost? It's by MP times labor rate, which we will get CB. And labor rate, maybe it would adjust in real time, and maybe it will not be $40 an hour right now. And then after doing all these, we can calculate the cost of the bending die. And in this slide, I would like to talk about the individual dies for deep drawing, which is also an important metal sheet stamping process. And deep drawing is a sheet metal forming process that transforms flat blanks into deep hollow shapes by pulling the material into a die cavity, and which is shown in the figure right here. And then as for the cost estimation for deep drawing, we will still calculate the total manufacturing points, MP. And we need to know that the MP right here is different from the previous one. Is equal to FLW times MP0 times FD. And FLW right here is the plane area correction factor, which we just introduced in the previous slide. And MP0 is equals to 28 plus 1.03 XP. And as for FD, is equals to 1.3, just for deep drawing. There, in this case, you can compare with the previous slide. We got FD equals to 1 for blanking die, 0.91 for part of die, and 0.88 for cut off die. Here is something that we need to notice during the calculation. Next, in this page, I would like to talk about miscellaneous features. And first is lens. It's a partial shear cut in the sheet metal that does not fully detach material, which is shown in the figure right here. And the second one is depression. It's a shallow indentation formed by pushing the metal into a cavity using matched punch and die. And here's the reference for the picture. And in the next page, another miscellaneous feature is embossed area. It's a raised or recessed pattern formed by compressing the sheet between matched dies, which is shown in the figure on the right. And another one is the hole flanges. It's produced by pressing a taper or bullet-nosed cylindrical punch into a smaller punched hole. And as for the cost estimation for miscellaneous features, we need to know MPX. MPX is the additional hours of punch and die machining. And in this equation, the only parameter that we need to know is NSP. And NSP is the total number of separate surface patches to be machined on punch faces and matching die surfaces. Thank you for listening to my presentation.